Yeah, I'll start. I'll speak in English. I'll say as follows. I received a PhD in computer science about 2 years ago, and people ask, oh, you must love technology, and my answer is actually not so much. I joke around and say I don't own a smartphone, I own a dumb phone. Right, a very simple phone that does nothing but makes phone calls. And I use as my GPS a sheet of paper with written directions. And my e-reader is just a printed book. And that's how I like it in life. So why did I get into computer science in the first place? It's because when I was 8 years old, my elementary school bought its first computer, the Commodore PET, which is a very simple computer. And from then on, I've been very involved in computers and computer science. I found it came very naturally to me, and I enjoyed it. But I was looking for something a lot more personal. So I decided to start teaching about 12 years ago at Queens College in the City University of New York. And I found that I very much enjoy the classroom experience. And I found that some of my students enjoyed it too, that they really enjoyed my presence in the class more than the material I was actually teaching. And I found that this is what I wanted to do with myself. So people ask, what is computer science? So this is what I wanted to get into today, a little bit, give you a little taste of what it means to say computer science. Because there's no chemistry lab, there are no microscopes, so what is the science that we're actually dealing with? And I like to say that computer science is really a study of computing. Like, what can we actually do with a computing device? And you look at it from a theoretical perspective, you can look at it from more of a practical perspective, but the point is, what can be done with something if you can build a computing device, which we have? What can you actually do with it? So I work more in the area of theoretical computer science. And maybe I made a little mistake today, but I figured I'll give you some technical overviews, and we'll see if we can take you through it. So we'll start with an example of what I mean here about analysis, in this case, of an algorithm. What do we mean by analyzing algorithms? Let's take an example as follows. Let's say you're walking in the street and see falafel for 14 shekel, and you want to know, is this a good price? How would you find out? Well, you know, in certain places. So you say, well, how would I know? So you say, I can go to every store in town and find out, and if this is the best price or is the good price, then I'll know. But you don't have the time to go to every store in town, so what else can you do? So you'll say as follows. Well, let's look at what they put into the falafels, the hummus, the trina, the chips, salat, everything. Comes out to maybe 7 shekel. So you know that if they're selling it for 14 shekel, they're only selling it for more than twice the price. What could be the minimum price is 7 shekels. They're only selling it for twice what the minimum price could be. So now you ask yourself the following. Well, maybe nobody has it for less. Maybe this is the best price they can get. But now all you got to do is find one store that sells it for 7 shekel, and then you know, okay, they're selling it to you for no less than twice the minimum price.
No, they're 6.
They changed the price to 7. So, well, I can't find it for 7. I can't use. Anyway, so here's an example from computer science. Okay, we call this vertex cover, and you have a graph with vertices and edges, right? The circles are the vertices, the lines are the edges that connect the vertices. And what you want to do is select the smallest number of vertices to cover all of the edges in the graph. Right, so here, if you select the red edges, the red vertices, those cover the red edges. The blue vertex covers those 3 blue vertices, and then the green vertex covers those two green edges. And that's what it's called a vertex cover. We chose these 3 vertices to cover all these edges in the graph. Okay, we're technical now. So now we have an algorithm. What does our algorithm do? It says take an edge, take both vertices on those edges, and then cover whatever edges you can. Right, so we chose those 2 red vertices connecting that edge, and then those cover those 3 edges that we see over there. Now we choose another edge that we haven't chosen yet, hasn't been covered yet, and take both vertices at both ends and use those for our cover, right? And then finally we choose and we keep on doing this until all edges in the graph are covered. Technical, I hope you can follow this. This is our algorithm. So what do we say about this algorithm? We say, well, we had to have chosen at least one of the vertices on each end of each of the edges that we selected, so we know that we chose no more than 2 of the minimum number of vertices that we need to cover all the edges in the graph. But now we have an example, the one that we have here, where we say that we could have been satisfied with 3 vertices, and we chose 6. We say we can't guarantee anything less than twice the minimum number of vertices with this algorithm that we had for doing a vertex cover. So I hope you don't mind the technicality of this, but this is kind of what we do in computer science in the theoretical perspective. We want to take the algorithms and pick them apart, to figure out what's the performance, how well we can do with them. So remaining things that you can do in computer science besides the theoretical analysis is also, let's say, systems, where you're trying to design systems and test them, push them to their limits and see what you can do with them. And there's artificial intelligence, which is a very large area, expands a lot of things and just keeps on multiplying and expanding. And that's about it, what I have to say. If you have any questions, you can be in contact with me. I'm looking for a job, if anyone has anything. But I know it's not the purpose of this, but thank you very much.
Thank you very much.